What if everything we thought we knew about the universe was just the tip of the iceberg? Picture this. You're standing on the shore of an endless cosmic ocean, staring out at the vast expanse of space, confident that the laws of physics, those reliable rules that govern everything from falling apples to orbiting planets, hold true everywhere. But what if they don't? What if, beyond the familiar glow of our Milky Way, the universe starts playing by a different set of rules? This isn't a thought experiment or a sci-fi plot. It's the startling reality astronomers are grappling with right now. For centuries, we've trusted physics to explain the cosmos, from Newton's gravity to Einstein's relativity. But today, at the farthest edges of the observable universe, something strange is happening. Galaxies are moving in ways they shouldn't. The fabric of space itself is stretching faster than our equations predict. Even the constants we thought were unchanging might not be so constant after all. It's as if the universe is whispering secrets that defy our understanding, leaving scientists with more questions than answers. How can the rules that work so perfectly here on Earth fail so spectacularly out there? This is the crisis in modern cosmology, a puzzle so profound it threatens to rewrite the textbooks. Dark energy's mysterious push, the Hubble tension's stubborn discrepancy, the unsettling gaps in our cosmic models, they all point to one unsettling possibility. We might be missing something fundamental about how the universe truly works. But here's the exciting part. Every great mystery is a chance for a breakthrough. In this video, we'll journey to the edge of known physics, explore the cracks in our current paradigms, and ask what these cosmic anomalies reveal about the nature of reality itself. Buckle up, because by the end, you'll never look at the night sky the same way again. To appreciate just how baffling these cosmic anomalies are, we need to rewind the clock and see how our understanding of the universe came together in the first place. For over 100 years, two towering pillars of physics, Einstein's general relativity and quantum mechanics, have shaped our cosmic rulebook. Relativity beautifully explains the dance of massive objects, from falling apples to colliding black holes, while quantum mechanics reveals the bizarre, probabilistic world of the ultra-small. Together, they form the standard model of cosmology, a framework so successful it predicted the Big Bang's afterglow and mapped the universe's expansion history with stunning precision. But here's the catch: the deeper we look, the more the universe seems to be thumbing its nose at these very rules. Take galaxy rotation, for example. According to our equations, stars on the outer edges of spiral galaxies should move slower than those near the center, just like planets farther from the Sun orbit more sluggishly. Yet when astronomers like Vera Rubin measured these rotations in the 1970s, they found something shocking. Stars at the edge were whipping around just as fast as those near the core. It was as if some invisible hand was propping them up, a mystery we now call dark matter. Then there's the universe's expansion. In the late 1990s, two teams studying distant supernova made an even more startling discovery. Not only is the cosmos growing, but it's doing so at an ever-increasing rate, as if pushed by some unseen energy. Dark energy entered the lexicon, and with it, a profound realization: our equations were missing something fundamental. These aren't minor hiccups, they're seismic tremors shaking the foundations of physics. The standard model, for all its triumphs, can't explain why 85% of matter is invisible, or why space itself is stretching faster than our math allows. Even more unsettling, the Hubble tension, a growing rift in measurements of how fast the universe is expanding. Some telescopes peg the number higher, others lower, and no amount of recalibrating closes the gap. It's like two clocks ticking at different speeds, and we can't figure out which one's broken. So where does this leave us? At a crossroads where every observation hints at a deeper layer of reality we've yet to uncover. Maybe dark matter and dark energy are clues pointing to new particles or forces. Maybe gravity itself works differently across cosmic distances. Or perhaps, as some theorists suggest, we're glimpsing the frayed edges of our current theories, where relativity and quantum mechanics finally meet and fail. One thing's certain, the universe is far stranger, far more mischievous than we ever imagined. And that's what makes this moment in science so thrilling. Imagine measuring the speed of a car with two different radar guns, only to get wildly different readings every single time. That's essentially the dilemma astronomers face with the Hubble tension, a discrepancy so persistent it's thrown modern cosmology into disarray. On one side, we have meticulous measurements of nearby stars and galaxies, where pulsating Cepheid variables act like cosmic lighthouses, their predictable brightness revealing distances. These local observations suggest the universe is expanding at about 73 kilometers per second per megaparsec, a speed that would make sense if dark energy's push were constant. But then we look back in time to the faint afterglow of the Big Bang itself, the cosmic microwave background, and the story changes. Here, the data insists the expansion rate is slower, closer to 67. The difference might seem small, but in a universe governed by precise laws, it's like two conflicting blueprints for the same building. What makes this mismatch so troubling isn't just the numbers, it's the fact that both methods are rock solid in their own right. Cepheids have been the gold standard for distance measurement since Henrietta Leavitt unlocked their secrets over a century ago, while the cosmic microwave background is arguably the most pristine snapshot of the early universe we'll ever have. If both are correct, then something fundamental in our cosmic equations must be wrong. Maybe dark energy isn't the static force we assumed, but is instead growing stronger over time, like a mysterious wind picking up speed. Or perhaps there's an undiscovered particle, a sibling to dark matter, tugging at the fabric of space in ways we haven't accounted for. Some theorists even speculate that gravity itself might weaken over vast distances, subtly altering the universe's expansion in a way our current models can't capture. The implications are staggering. If the Hubble tension holds, it could mean our entire cosmic timeline, the age of the universe, the fate of galaxies, even the nature of dark energy, needs a rewrite. It's like discovering the clock you've been using to time everything is running fast or slow, throwing all your schedules into chaos. And while some scientists hope the tension might dissolve with better data or refined methods, each new observation only deepens the mystery. The James Webb Space Telescope, with its razor-sharp infrared vision, recently confirmed the local measurements, leaving us with an even sharper contradiction to resolve. This isn't just academic nitpicking, it's a rare crack in the armor of our understanding, a glimpse into the unknowns lurking beyond the edges of current physics. Whether the answer lies in revised theories, exotic particles, or something entirely unforeseen, one thing is clear: the universe is still holding back its deepest secrets. And that's what makes this moment so electrifying. Every discrepancy is a clue, every tension a signpost pointing toward the next great leap in our cosmic story. Dark matter is the universe's most frustrating magic trick, an invisible force we can't see, touch, or directly detect, yet its fingerprints are everywhere. Think of it like the wind. You don't see it, but you watch leaves swirl in its grasp. For galaxies, those leaves are stars, orbiting so fast they should fling into the void, yet something unseen holds them in place. That something is dark matter, a cosmic scaffolding that makes up 85% of the universe's matter. Without it, galaxies would fly apart, and the cosmos as we know it wouldn't exist. But here's the kicker. After decades of searching, we still don't know what it actually is. The hunt for dark matter reads like a scientific detective story with endless red herrings. Particle physicists have scoured underground labs waiting for hypothetical WIMP, weakly interacting massive particles, to bump into ordinary atoms. Others have tuned massive detectors to catch actions, ghostly particles that might flit through space like cosmic whispers. But so far, nothing. No signal, no shadow, no definitive proof. This silence has led some researchers to question the very premise. What if dark matter isn't a particle at all? Enter modified Newtonian dynamics, a radical idea that suggests gravity works differently on galactic scales. Instead of invoking invisible matter, Mund tweaks the math, arguing that our understanding of gravity is incomplete. At first glance, it's elegant, no need for unseen substances, just a cosmic correction to Newton's laws. But Mund has its own ghosts. While it explains some galaxy rotations beautifully, it stumbles over larger cosmic puzzles, like the way galaxy clusters bend light or how the early universe clumped into today's vast web. Dark matter, for all its mystery, fits these pieces better. Then there's the bullet cluster, a cosmic collision where galaxies and their gas clouds smashed apart, leaving their gravity traced by warped starlight, offset from visible matter entirely. It's as if two invisible giants passed through each other, unfazed. Mund struggles to explain this. Dark matter doesn't blink. The plot thickens when supercomputers simulate the universe with dark matter. These virtual cosmos birth galaxies eerily similar to ours, yet the details often don't match. Real galaxies have fewer satellite galaxies than predicted, and their cores are less dense. It's like baking a cake with a perfect recipe, only to open the oven and find the textures all wrong. Could dark matter interact with itself in ways we haven't modeled? Or are we missing a deeper layer of physics altogether? One thing's certain: the longer dark matter evades detection, the more tantalizing the alternatives become. Maybe it's not one thing but many, a shadowy zoo of particles, each leaving faint traces. Or perhaps, as some theorists speculate, it's tied to extra dimensions or primordial black holes forged in the Big Bang's first moments. Every dead end forces us to rethink, and that's where the real excitement lies, because whether dark matter is a particle, a flaw in gravity, or something beyond our current imagination, solving this riddle won't just fill a gap in our equations, it'll rewrite the story of the cosmos itself. Dark energy is the universe's ultimate wildcard, a force so enigmatic it makes dark matter seem almost predictable. While dark matter tugs at galaxies, holding them together, dark energy does the opposite. It pushes space itself apart, accelerating the expansion of the cosmos in a way that defies intuition. Imagine blowing up a balloon with dots on its surface. Now picture the dots not just moving apart as the balloon expands, but speeding up, as if some unseen hand were pumping air in faster and faster. That's the unsettling reality we're facing. The story of dark energy begins with a cosmic mea culpa. Einstein originally introduced the cosmological constant, a fudge factor in his equations, to keep the universe static, a notion he later called his greatest blunder when Edwin Hubble discovered the universe was expanding. But in the late 1990s, astronomers studying distant supernovas stumbled onto something even more shocking. The expansion wasn't just continuing, it was accelerating. The cosmological constant was resurrected overnight, rebranded as dark energy, and suddenly we had a new mystery on our hands. What makes dark energy so baffling is its sheer dominance. It accounts for roughly 68% of the universe's energy budget, dwarfing even dark matter. Yet unlike matter, whether dark or visible, it doesn't clump or interact. It's a property of space itself, a repulsive force woven into the fabric of reality. The simplest explanation is Einstein's cosmological constant, a steady, unchanging energy density permeating the vacuum of space. But what if it's not constant at all? Some theories suggest dark energy could evolve over time, growing stronger or weaker, reshaping the fate of the cosmos in ways we can't yet predict. The stakes couldn't be higher. If dark energy strengthens, it could eventually tear galaxies, stars, and even atoms apart in a big rip. If it weakens, gravity might regain the upper hand, collapsing the universe in a big crunch. And if it's truly constant, the cosmos will expand forever, fading into cold, empty darkness. Right now, our best clues come from painstaking measurements of supernova, galaxy clustering, and the cosmic microwave background. But each new dataset seems to add more questions than answers. For instance, why does dark energy's apparent density match the vacuum energy predicted by quantum theory? But only if you're off by a factor of 10 to the power of 120. It's like calculating the weight of a feather and getting the mass of a galaxy instead. This discrepancy hints at something profound. Our understanding of gravity, quantum mechanics, or even the nature of space itself might be fundamentally incomplete. Some theorists propose exotic solutions like quintessence, a dynamic field that changes over time, or modifications to general relativity on cosmic scales. Others wonder if dark energy is a sign of extra dimensions or a shadow of another universe bleeding into ours. The truth is, we're groping in the dark, and every attempt to shine a light only reveals how much we still don't know. Yet this uncertainty is what makes cosmology so thrilling. Dark energy isn't just a puzzle, it's a gateway to deeper laws of physics waiting to be uncovered. Whether it's a constant, a variable, or something beyond our current imagination, one thing's certain: the universe is far stranger, far more dynamic than we ever dreamed. And that's the beauty of the unknown. It keeps us reaching, questioning, and marveling at the cosmos' endless mysteries. If our current cosmic models were a recipe for galaxy formation, we'd be staring at a failed dish, one where the ingredients just don't mix the way the cookbook promised. Take the missing satellites problem. Supercomputer simulations built on dark matter's rules predict a bustling neighborhood of tiny dwarf galaxies orbiting larger ones like the Milky Way. But when astronomers peer into the sky, they find far fewer of these cosmic minnows than expected. It's like opening a box labeled 1,000 marbles and finding only a handful inside. The glitches don't stop there. Some galaxies appear impossibly ancient, their stars shining bright in the cosmic dawn when the universe was barely a toddler. Others are bizarrely massive, defying the timeline of how quickly matter should have clumped together after the Big Bang. And then there's the clustering mystery: galaxies bunch up in ways our simulations struggle to replicate. It's as if the universe ignored the instruction manual and assembled itself haphazardly. So where's the disconnect? One possibility is that dark matter isn't as simple as we've modeled. Maybe it's warmer and moving faster in the early universe, smearing out the seeds of small galaxies before they could fully form. Or perhaps it interacts with itself, creating friction that alters how structures emerge. Then there's the wild card of feedback. Supermassive black holes and exploding stars blast energy into their surroundings, potentially sterilizing entire regions of space, preventing small galaxies from ever coalescing. But the most tantalizing and unsettling idea is that we're missing a fundamental piece of physics. Could gravity behave differently in the vast emptiness between galaxies? Are we underestimating the role of magnetic fields or cosmic rays in shaping galactic evolution? Every mismatch between simulation and observation is a breadcrumb leading us toward a deeper truth. And while the answers aren't clear yet, one thing is, the universe is far more inventive, far more unruly than our best models can capture. And that's what makes this crisis not just a problem, but an invitation to discover something extraordinary. Between the glittering threads of galaxies that weave our cosmic web, there are vast deserts of nothingness, regions so empty they could swallow thousands of Milky Ways without a trace. These are the cosmic voids, the universe's silent giants, stretching hundreds of millions of light years across with barely a galaxy to break the monotony. But here's the twist: these voids aren't just passive gaps. They're expanding faster than our physics says they should, as if gravity itself is taking a vacation in the emptiness. Take the KBC void, a colossal bubble of relative nothingness where our Milky Way just happens to reside. It's like living in a secluded valley while the rest of the cosmos thrives in bustling metropolises. Measurements suggest this void is 7 times wider than average, with matter densities strikingly lower than the cosmic norm. If that's true, it means we're cosmic outliers, observing the universe from inside a rare underdensity, a realization that throws a wrench into how we calculate everything from expansion rates to dark energy's influence. Imagine trying to gauge Earth's climate by standing in a desert. Your data would be hopelessly skewed. The mysteries deepen when we watch how voids evolve. According to general relativity, these regions should expand slowly, their growth tempered by the feeble gravity of the sparse matter within them. Yet observations reveal they're stretching far quicker than predicted, almost as if space itself is more elastic here. Some theorists argue this could be evidence for modified gravity, a tweak to Einstein's equations that kicks in on galactic scales. Others wonder if voids are hiding unseen forces, like dark energy pooling in these emptiness, pushing them apart with extra vigor. Then there's the unsettling possibility that voids aren't just oddities but central players in cosmic evolution. Their rapid expansion might be sculpting the universe on the grandest scales, tugging at galaxy clusters like invisible hands shaping dough. If so, our models of cosmic structure built on the assumption of uniform expansion might be missing a critical chapter. Even more provocative is the idea that voids could be fossils of the early universe, relics of primordial ripples that dictated where matter would clump and where it would vanish. What's clear is that these cosmic deserts are anything but barren of intrigue. They challenge our understanding of gravity, question our place in the cosmos, and might even hold clues to dark energy's true nature. Whether they're revealing new physics or simply reminding us of how atypical our corner of existence might be, one thing's certain: the voids are speaking. And if we listen closely, they might just rewrite the rules of the universe. At the heart of modern physics lies an embarrassing secret. Our two most successful theories are fundamentally at war with each other. Quantum mechanics, which governs the subatomic world with its probabilistic dances and particle-wave duality, operates by rules that seem alien to general relativity's smooth, geometric vision of spacetime. Both work flawlessly in their own domains: quantum mechanics predicting particle behavior with unimaginable precision, relativity explaining cosmic phenomena like black holes and gravitational waves. But when these realms collide, as they inevitably do in the most extreme corners of the universe, the result isn't a grand unification, it's mathematical chaos. Take black holes, those cosmic paradoxes where both theories are pushed to their breaking points. According to relativity, A black hole's core crushes matter into an infinitely dense singularity, a point where space-time curvature becomes infinite and physics simply stops making sense. But quantum mechanics insists that information, the fundamental identity of particles, can never be truly destroyed. So when matter falls into a black hole, does it vanish into oblivion at the singularity, or is its information somehow preserved as quantum rules demand? This information paradox has stumped physicists for decades, with luminaries like Stephen Hawking and Leonard Susskind debating fiercely over the implications. The clash isn't just academic, it suggests that deep down our understanding of reality is missing a critical piece. The Big Bang presents a similar puzzle. If we rewind cosmic expansion to time zero, we again confront a singularity, a moment where all the universe's mass and energy were crammed into an infinitely hot, dense point. But here, both quantum mechanics and relativity fail spectacularly. Quantum fluctuations should have been unimaginably violent at these scales, yet relativity treats the early universe as a smooth, expanding fabric. How can both be true? It's like trying to describe a hurricane with the mathematics of a calm pond. Desperate for solutions, physicists have proposed audacious frameworks. String theory suggests that particles aren't dots but tiny vibrating strings, with their harmonies generating all forces and matter. In this symphony, gravity might finally find its quantum counterpart. But strings require extra dimensions, possibly 10 or more, curled up so small we'll never perceive them. Then there's loop quantum gravity, which reimagines space-time itself as a woven fabric of discrete loops, eliminating singularities by making the universe pixelated at the tiniest scales. Both ideas are mathematically elegant, but neither has produced testable predictions, leaving them in theoretical limbo. The stakes couldn't be higher. If we uncover how these theories unite, it might illuminate cosmology's greatest mysteries: dark energies push, dark matters pull, even the universe's ultimate fate. Some speculate that quantum gravity could reveal hidden layers of spacetime, or that the cosmic constant isn't constant at all but fluctuates due to deeper quantum processes. Others wonder if the very fabric of reality operates differently under extreme conditions, with gravity weakening or strengthening in ways we've never imagined. What's certain is this: until we resolve the quantum relativity divide, our cosmic map will remain incomplete. Every black hole, every relic of the Big Bang, every discrepancy in our models is a signpost pointing toward a deeper truth. And when that truth finally emerges, it won't just reconcile equations, it'll redefine our place in the universe. Imagine flipping a coin 1,000 times and getting heads every single time, not just once, but in a perfect, eerie line across the sky. That's the level of cosmic weirdness astronomers are confronting with the so-called axis of evil, a bizarre pattern etched into the universe's oldest light. The cosmic microwave background, that faint afterglow of the Big Bang, should be a nearly uniform tapestry of temperature fluctuations, tiny ripples from the universe's fiery infancy. But when scientists mapped it with satellites like Planck and WMAP, they found something unsettling. Hot and cold spots aren't scattered randomly. Instead, they appear loosely aligned along a mysterious axis, as if the universe itself has a hidden spine. This isn't just a statistical hiccup. The alignment defies the cosmological principle, a bedrock assumption that the universe is homogeneous and isotropic, meaning it looks roughly the same in all directions, no matter where you're standing. If the axis of evil is real, it implies our cosmos might have a preferred direction, a cosmic north that challenges the very notion of universal fairness. Some researchers dismiss it as an artifact of measurement errors or galactic dust interfering with our telescopes, but the pattern persists even after meticulous cleanup, leaving scientists to grapple with far wilder explanations. Could it be a shadow of a universe that existed before our own, imprinting its structure onto the newborn cosmos, or evidence of exotic physics warping space-time on scales we can barely comprehend? The implications are dizzying. If the universe isn't uniform, our calculations for everything from dark energy's strength to the fate of galaxies might be skewed by an unaccounted-for cosmic tilt. Even more provocative is the idea that the axis of evil could be a window into multiverse theories, where our universe is just one bubble in a frothing sea of others, each with its own physics. Picture a soap bubble colliding with another in a sink. The dent left behind might look like an axis to those inside. Yet for all its intrigue, the axis of evil remains controversial. Critics argue that human brains are wired to find patterns, even in randomness, and that we're seeing cosmic pareidolia, like spotting faces in clouds. But with each new dataset, the anomaly refuses to vanish entirely, leaving astronomers divided. Whether it's a flaw in our models or a fingerprint of something deeper, one thing's clear: the universe keeps handing us puzzles that defy our neatest theories. And in that defiance, there's an irresistible invitation to look harder, think deeper, and question everything we thought we knew. When the cosmic rulebook starts falling apart, sometimes you don't just need new pages, you need a whole new book. That's the bold thinking behind alternative theories challenging the standard model of cosmology, where physicists are tossing out old assumptions and rebuilding reality from the ground up. Take Eric Verland's theory of emergent gravity, for instance. It suggests gravity isn't a fundamental force at all, but a side effect, a sort of cosmic illusion emerging from the way information is structured in spacetime. Picture a crowded concert. The movement of the crowd isn't dictated by some invisible force, but by countless individual decisions. Similarly, Verland argues, gravity might be the collective behavior of microscopic bits of information we can't yet see. It's an elegant idea that could explain away dark matter entirely, but here's the catch. When tested against the motions of galaxies, emergent gravity nails some predictions but flounders on others, like the way galaxy clusters bend light. It's as if the theory solves one puzzle by jamming another piece out of place. Then there's the holographic principle, a radical notion that our three-dimensional universe might be a projection of information stored on a distant, two-dimensional surface. Think of it like a movie screen. The images appear to have depth, but everything you're seeing is encoded in flat pixels. If true, this would mean reality is fundamentally informational, with gravity and quantum mechanics unified at some deeper, unseen layer. The math is dazzling, but the theory struggles with practical tests. How do you prove we're living in a cosmic hologram when the screen might be billions of light years away? Even more audacious are ideas like massive gravity, which suggests gravitons. The hypothetical particles carrying gravity have mass, subtly altering how the force behaves across cosmic distances. Or variable speed of light theories, where light in the early universe raced faster than today, potentially explaining why distant regions appear eerily uniform. These aren't just tweaks, they're full-scale revolts against Einstein's relativity, yet each comes with trade-offs. Massive gravity, for example, predicts ghostly instabilities in spacetime that have never been observed, while variable light speed risks contradicting well-tested nuclear physics. The biggest hurdle: many of these theories excel at solving one cosmic anomaly but crumble when faced with another. It's like patching a leaky boat: fix one hole and water gushes in elsewhere. That's why some physicists argue we're not witnessing a paradigm shift so much as a period of creative chaos, where bold ideas are stress-tested until only the strongest survive. Others, though, see glimmers of hope. The James Webb Telescope's glimpses of unexpectedly mature early galaxies, for instance, could hint at physics beyond our models, perhaps even signs of these exotic alternatives. What's undeniable is this: the cracks in the standard model have flung open the doors to wild, wonderful possibilities. Whether any of these theories will rewrite cosmology or fade into footnotes, they're proving one thing: our universe is stranger, more inventive than any single framework can capture. And in that uncertainty lies the thrill of discovery. What if the universe's greatest illusion isn't dark matter, but gravity itself? For decades, we've assumed that Einstein and Newton's equations hold true everywhere, from Earth to the edge of the cosmos. But what if gravity, the force we thought we understood, starts playing by different rules when you leave our galactic neighborhood? That's the radical premise of modified Newtonian dynamics, or a theory that dares to rewrite the laws of gravity to explain away dark matter entirely. At its core, MUND is elegantly simple. Instead of invoking invisible particles to explain why stars on the outskirts of galaxies orbit too fast, it suggests gravity doesn't fade as quickly over vast distances as Newton predicted. Below a certain ultra-weak threshold, about 10 trillion times gentler than the gravity holding you to Earth, the force tapers off differently, giving stars an extra nudge. No dark matter required, and here's the kicker: for individual galaxies, MUND works shockingly well. It predicts rotation curves with uncanny precision, matching observations of spirals from Andromeda to distant dwarfs. It's as if someone found a hidden setting in gravity's code, one that perfectly solves a mystery that's baffled astronomers for 50 years. But the moment we zoom out to cosmic scales, MUND's shine starts to tarnish. Galaxy clusters, those sprawling metropolises of hundreds of galaxies bound together, still seem to need extra mass to explain their motions and the way they bend light. The Bullet Cluster, where two galaxies collided and left their gravity visibly divorced from visible matter, is particularly damning. MUND struggles to explain this separation without invoking, you guessed it, some form of invisible mass. Enter TVS, a more sophisticated cousin of MUND that tweaks Einstein's relativity itself, weaving in extra fields to mimic dark matter's effects. It's like adding gears to gravity's engine, making it flexible enough to handle both galaxies and clusters. But even TVS stumbles when faced with the universe's largest structures or the precise patterns in the cosmic microwave background. The debate gets even thornier when we consider timing. MUND beautifully explains mature galaxies but falters when simulating how the cosmos evolved from the Big Bang to today. Supercomputer runs with dark matter effortlessly grow cosmic webs resembling our universe, while MUND-based simulations often produce structures that look off. Too clumpy here, too sparse there. It's like baking a cake with an alternative recipe. It might rise fine, but the texture's all wrong. Yet MUND isn't ready for the scrap heap. Some researchers argue we've only scratched the surface of modified gravity's possibilities. What if MUND isn't the final answer but a clue pointing toward a deeper theory, one that blends gravity's quirks with something entirely new? Others suggest dark matter and modified gravity might both be pieces of a larger puzzle, with each explaining different cosmic phenomena. The real test will come from next-generation telescopes mapping the universe in unprecedented detail. If they find galaxies behaving in ways MUND can't tweak, the theory may fade. But if they uncover more anomalies, places where gravity clearly defies expectations, we might be on the brink of a revolution as profound as Einstein's overthrow of Newton. Either way, the takeaway is thrilling. Our understanding of gravity, the force that literally shapes the cosmos, is still up for grabs, and that means the universe has more surprises in store than we ever imagined. What if our universe isn't the only one, just a single page in an infinite cosmic library? where every book has its own set of physical rules. That's the breathtaking premise of the multiverse hypothesis, an idea that's gained traction as cosmologists wrestle with the eerie perfection of our universe's constants. Take the cosmological constant, the number governing dark energy's push. If it were even slightly stronger, galaxies would have been ripped apart before life could form. Slightly weaker, and the universe would have collapsed long ago. The odds of it being just right seem astronomically low unless, perhaps, ours is one of countless universes where every possible value plays out. The multiverse isn't just a sci-fi trope. It emerges naturally from theories like eternal inflation, where bubble universes endlessly sprout from a seething quantum foam, each with different laws. String theory takes it further, suggesting there could be 10 to the power of 500 possible vacuum states, each a unique universe with its own physics. In this sprawling landscape, our finely tuned cosmos isn't a miracle, it's a statistical inevitability. Somewhere in the multiverse, there's a version of reality where gravity repels, stars never ignite, or time runs backward. We just happen to live in the rare slice where conditions allow us to exist. But here's the rub: the multiverse might be forever beyond our reach. If other universes are causally disconnected, separated by horizons even light can't cross, how could we ever detect them? Critics argue this makes the hypothesis untestable, pushing it into the realm of philosophy rather than science. Nobel laureate David Gross dismisses it as a dangerous idea that could halt progress, letting researchers shrug away cosmic mysteries by saying, "That's just how things are in our patch." Even proponents admit the challenge. Without empirical evidence, the multiverse risks becoming a cosmic cop-out, a place where any inconvenient observation can be explained away as local variance. Yet the allure persists, especially as traditional cosmology hits roadblocks. When the James Webb Space Telescope spotted galaxies too mature for their age, some wondered if they were outliers in a broader multiverse distribution. Others speculate that anomalies like the axis of evil could be bruises from a long-ago collision with another universe. And while direct proof remains elusive, indirect signatures might exist like strange patterns in the cosmic microwave background or gravitational waves from primordial bubble collisions. The debate cuts to the heart of what science is. Is the multiverse a bold extension of physics or a philosophical Hail Mary? For now, it remains a tantalizing maybe, a reminder that the universe's greatest mysteries might not just lie in the stars, but in the spaces between realities we can't yet see. Until then, the multiverse stands as both a provocative escape and a challenge to keep searching, even when the answers slip beyond the horizon. Cosmic inflation was supposed to be the ultimate fixer, a theoretical band-aid that smoothed over the universe's roughest edges. Picture this: in the first trillionth of a second after the Big Bang, space itself ballooned faster than light, stretching quantum fluctuations into the seeds of galaxies and ironing out wrinkles in the cosmos. This single idea solved multiple puzzles at once. Why the universe looks so uniform in every direction, why it's geometrically flat, and why we've never found exotic relics like magnetic monopoles. Inflation became cosmology's golden child, its predictions matching the cosmic microwave background with jaw-dropping precision. But lately, cracks have started to show, and the deeper we look, the more this elegant solution feels like a house of cards. For starters, inflation doesn't explain itself. What triggered that explosive expansion? What made it stop? The theory relies on a hypothetical, inflaton field, a sort of cosmic accelerator pedal that mysteriously floored itself and then released its energy into particles. But we've never detected this field, and its properties seem suspiciously fine-tuned. It's like saying a car drove itself because we imagined a ghost pressing the gas. Even stranger, many inflation models predict not just one universe, but an infinite multiverse, a fractal foam of bubble universes, each with different physical laws. While that might sound thrilling, it's also scientifically frustrating. If anything can happen somewhere in the multiverse, how do we test what's uniquely true about our own? Then there's the data. The cosmic microwave background, inflation's crowning jewel, has started whispering contradictions. Certain large-scale patterns, like the infamous axis of evil, don't quite fit the classic inflation story. Some regions of the sky appear anomalously cold or hot, as if the universe didn't inflate as evenly as we thought. Even the distribution of galaxies on colossal scales seems slightly off, with structures too vast to have grown so quickly under standard inflation timelines. It's as if the universe left us a recipe, but we're finding extra ingredients in the bowl. The most damning critique: inflation has become so flexible that it risks explaining nothing at all. With hundreds of possible models, each tweaking the inflaton's behavior to match new observations, the theory starts to feel unfalsifiable. When a hypothesis can accommodate any outcome, does it really predict anything? Nobel laureate Paul Steinhardt, once an inflation pioneer, now calls it a theory in crisis, arguing that it's drifted from its scientific roots into untestable speculation. So what's the alternative? Some theorists are revisiting bouncing cosmologies, where the Big Bang wasn't a beginning but a rebound from a previous contraction. Others explore emergent universes that condense from a timeless quantum foam, no inflation required. There's even a wild idea called conformal cyclic cosmology, where the universe's distant future becomes the next Big Bang in an endless loop. These ideas are fringe now, but so was inflation once. The real lesson here isn't that inflation is wrong. It's that science thrives when its best ideas are challenged. Every anomaly, every stubborn discrepancy is a chance to dig deeper. Whether inflation survives or falls, the questions it raised have already reshaped our cosmic perspective. And that's the beauty of the scientific journey. Sometimes the most useful theories aren't the ones that last, but the ones that push us to think beyond them. Black holes are cosmic shredders, or so we thought. According to Einstein's general relativity, anything that crosses a black hole's event horizon is lost forever, crushed into a singularity where space and time cease to make sense. But quantum mechanics, the rulebook for the subatomic world, insists that information, the fundamental identity of particles, can never be truly destroyed. This clash is the black hole information paradox, a puzzle so profound it's forced physicists to question the very nature of reality. The paradox sharpened in the 1970s when Stephen Hawking showed that black holes aren't entirely black. They leak radiation, slowly evaporating over eons. But here's the catch: Hawking radiation appears random, carrying no trace of the material that fell in. If a black hole vanishes entirely, leaving only this thermal static behind, what happened to all the information it swallowed? It's like burning a library and claiming the smoke particles somehow encode every book's contents. A notion that violates quantum mechanics' core tenet of unitarity, which demands information preservation. For decades, physicists hoped the answer lay in the radiation itself, that subtle quantum correlations might somehow stash the missing data. But in 2012, a bombshell dropped. Theorists proposed that black holes might have firewalls, furious walls of energy just inside the event horizon that obliterate anything passing through. The idea was radical. Either Hawking was wrong about radiation's randomness, or Einstein was wrong about the smoothness of space-time near the horizon. Neither option was palatable. Firewalls implied that the laws of physics change depending on where you stand, a violation of relativity's equivalence principle. which says free fall should feel like floating in empty space. Enter holography, an even wilder idea. Inspired by string theory, the holographic principle suggests that all the information in a black hole isn't lost inside but smeared across its event horizon, like a cosmic fingerprint. In this view, the three-dimensional universe we perceive might be a projection of data encoded on a distant two-dimensional surface. If true, black holes don't destroy information, they transform it, translating matter into a sort of celestial braille we don't yet know how to read. Recent breakthroughs in calculating this holographic entropy have lent credibility to the idea, but mysteries remain. How does the information escape? And what does it look like once it does? The stakes couldn't be higher. Solving the paradox wouldn't just tidy up black hole physics. It could reveal the missing link between gravity and quantum mechanics, a theory of quantum gravity that's eluded us for a century. Some speculate the answer lies in wormholes, tiny quantum bridges that might secretly ferry information out of black holes. Others suggest space-time itself is woven from entangled quantum bits, meaning information was never truly inside the black hole to begin with. One thing's certain, the paradox is more than a theoretical curiosity. It's a flashing signpost pointing toward a deeper layer of reality, where space-time, information, and quantum weirdness collide. And as we peel back the layers, we might just find that black holes aren't cosmic dead ends, but the key to unlocking the universe's deepest secrets. We like to think of our cosmic measurements as precise and infallible. After all, science thrives on data. But what if the very tools we use to study the universe are subtly distorting the picture? Consider redshift, the stretching of light from distant galaxies that tells us how fast they're moving away. For a century, redshift has been our cosmic speedometer, the key to mapping the universe's expansion. Yet even this bedrock measurement might not be as straightforward as we thought. Some astronomers argue that unrecognized errors like light interacting with interstellar dust or quantum effects we don't yet understand could skew redshift readings, making galaxies appear farther or faster than they truly are. It's like trying to judge a car's speed through foggy glasses. You might be close, but you're not seeing the full picture. Then there's calibration bias, the silent gremlin lurking in our instruments. Telescopes are built and tuned using known standards, stars, distances, and physical constants we assume are fixed. But what if those standards aren't as universal as we believe? The Hubble constant controversy, where different telescopes give conflicting expansion rates, might stem not from cosmic mysteries, but from tiny discrepancies in how we calibrate our devices. Imagine two chefs using slightly different tablespoons to measure ingredients. Their cakes might rise differently, even with the same recipe. Similarly, if the James Webb Space Telescope and Planck satellite are reading the cosmos with imperceptibly different yardsticks, their conflicting results could reflect human error, not celestial rebellion. Even more unsettling is the specter of incomplete data. Our view of the universe is like peering through a keyhole. We only see a fraction of what's out there. Galactic dust clouds obscure vast regions, while the universe's accelerating expansion ensures light from the most distant reaches will never reach us. Could missing pieces of the cosmic puzzle explain why our models feel increasingly strained? For instance, if we've underestimated the number of dwarf galaxies or overlooked hidden structures, our calculations for dark matter's distribution might be wildly off. It's like trying to reconstruct a symphony by listening to just the violin section. You'll miss the harmonies that give the full composition its richness. The James Webb Space Telescope, with its unprecedented infrared vision, promises to cut through some of this noise, but even its dazzling clarity comes with caveats. Every instrument has blind spots, and every dataset carries assumptions. If history teaches us anything, it's that each leap in observational power reveals new layers of complexity, not just answers. The real breakthrough might not come from better tools alone, but from questioning how we interpret what they show us. After all, the universe doesn't owe us intuitive truth. It's our job to decode its whispers, even when they defy our expectations. And sometimes the most profound discoveries begin when we admit that our rulers might be bending. The next decade could be a turning point for cosmology, a moment when we either crack the universe's greatest mysteries or tumble deeper into the labyrinth. 3 groundbreaking missions are leading the charge: the Euclid Space Telescope, the Vera Rubin Observatory's Legacy Survey of Space and Time LSST, and the Square Kilometer Array SCAR Radio Telescope. Together, they're poised to map the invisible scaffolding of the cosmos with a precision that would have been unimaginable just a generation ago. But will these instruments bring clarity, or will they reveal even deeper layers of cosmic confusion? Euclid, launched by the European Space Agency, is designed to hunt dark matter and dark energy by mapping the shapes and distributions of billions of galaxies across 10 billion light-years. Using weak gravitational lensing, a phenomenon where dark matter bends the light from distant galaxies like a funhouse mirror, Euclid will trace the invisible web that binds the universe. If dark energy truly changes over time, Euclid might catch it in the act, revealing whether the universe's acceleration is steady or shifting. But there's a tantalizing risk. What if the data doesn't fit any of our models? Imagine opening a lock only to find the mechanism inside is nothing like you expected. Meanwhile, on a mountaintop in Chile, the LSST will take this hunt to warp speed. With its 3.2 gigapixel camera, the largest ever built, it'll scan the entire southern sky every few nights, creating a time-lapse movie of the cosmos. This isn't just about spotting asteroids or supernova, though it'll find millions. The LSST real power lies in detecting subtle changes in galactic motions and structures, potentially uncovering new clues about dark matter's behavior. But here's the twist: the more data we collect, the more we might realize how much we've been missing. Previous surveys were like studying a forest by counting trees from a distance. The LSST will let us track every leaf's flutter. And in that deluge of detail, anomalies we once dismissed as noise could emerge as glaring signals of new physics. Then there's the SKA, a radio telescope so vast it'll span 2 continents, with thousands of dishes in South Africa and 1 million antennas in Australia. By tuning into the faintest radio whispers from the early universe, the SKA could reveal how the first galaxies formed and how dark matter shaped their growth. But its most revolutionary potential lies in testing gravity itself. If Einstein's relativity wobbles at cosmic scales, the SKA's ultra-precise measurements of pulsars, nature's most accurate clocks, might catch gravity slipping. The stakes couldn't be higher. If these missions confirm our current theories, it'll be a triumph. But if they deepen the contradictions, cosmology could face a paradigm shift as profound as the Copernican revolution. Some theorists quietly hope for chaos because in science, the biggest breakthroughs come from the moments when the rulebook burns. Whether we're on the brink of clarity or chaos, one thing's certain: the universe isn't done surprising us. And that's what makes this golden age of discovery so exhilarating. When we hear phrases like, "the universe is fine-tuned for life," it sounds poetic, almost comforting. The idea suggests that the cosmos was tailor-made for beings like us, with physical constants so precisely calibrated that even a tiny shift would make stars, planets, and life itself impossible. But this interpretation often gets twisted into something far more misleading. The truth: the universe isn't fine-tuned for life. Life evolved within the universe's parameters. Think of it like a puddle marveling at how perfectly its hole fits its shape, unaware that it's the water that conformed to the space, not the other way around. Yes, the cosmological constant, the strength of gravity, and other fundamental forces appear exquisitely balanced, but that doesn't imply intent. It simply means we're here because these conditions allowed it, not because they were designed to. Another persistent myth, that dark matter is just a placeholder, a sign that scientists made a mistake. Critics argue, if you can't see it or detect it directly, maybe it doesn't exist at all. But dark matter isn't some lazy excuse for gaps in our knowledge. It's a conclusion drawn from overwhelming, cross-verified evidence. Galaxy rotations, gravitational lensing, the cosmic microwave background, all these phenomena point to the same invisible mass. It's like detectives finding fingerprints, footprints, and DNA at a crime scene, all pointing to the same suspect, even if that suspect remains unseen. The real debate isn't whether dark matter exists, but what it is: a particle, a modification of gravity, or something even stranger. Then there's the oversimplification that Einstein was wrong. While it's true that general relativity struggles to explain cosmic-scale anomalies, it's not because Einstein's theory is broken, it's because it's incomplete. Relativity still predicts everything from GPS satellite corrections to black hole shadows with stunning accuracy. The crisis in cosmology isn't about tossing out old ideas but expanding them. Much like Newton's laws still work perfectly for baseballs and rockets, even if they fail near black holes. Science isn't a series of overturned truths but layers of understanding, each building on the last. Perhaps the most dangerous misconception is that scientific consensus equals dogma, that researchers stubbornly cling to theories like dark energy or inflation out of tradition. In reality, cosmologists love tearing down paradigms. The entire field thrives on anomalies, with rival teams racing to poke holes in each other's work. When the Hubble tension emerged, scientists didn't ignore it. They dove headfirst into the discrepancy, questioning everything from telescope calibrations to the nature of dark energy. That's how science evolves, not by defending old ideas, but by relentlessly testing them against the universe's stubborn, messy reality. So why does dispelling these myths matter? Because misconceptions muddy the waters, turning nuanced debates into polarized shouting matches. When someone claims dark matter is a fudge factor, they're not just critiquing a theory, they're dismissing decades of meticulous observation. Conversely, treating fine-tuning as proof of design shuts down deeper questions about multiverses or emergent physics. The beauty of cosmology lies in its uncertainties, its open questions, the thrilling possibility that the next breakthrough might come from challenging assumptions, not clinging to them. And that's where critical engagement begins, not with easy answers, but with better questions. At the heart of every cosmic mystery lies a deeper question, not just about how the universe works, but what it means to be human in the face of such vast uncertainty. If our most trusted laws of physics crumble at cosmic scales, it shakes more than scientific models. It rattles our very understanding of reality. For centuries, we've assumed the universe operates by rules we can eventually decode, given enough time and ingenuity. But what if some truths are forever beyond our grasp? Not because we lack the right tools, but because reality itself is structured in ways our minds weren't built to comprehend. Consider the humble goldfish in its bowl. To it, the world is curved and distorted by the glass, its view limited to fleeting shadows passing by. Could we be like that fish, mistaking our limited perspective for ultimate truth? The crisis in cosmology forces us to confront this possibility. Dark matter's invisibility, dark energy's push, even the Hubble tension. They might not just be puzzles waiting for solutions, but signs that our laws of physics are merely local bylaws, applicable only to our cosmic neighborhood. It's a humbling thought. The universe isn't obligated to make sense to us. This isn't just scientific speculation, it's a philosophical earthquake. If the cosmos operates by rules that defy human logic, what does that say about our quest for knowledge? Are we explorers mapping undiscovered territory, or ants trying to decipher a symphony? Some argue that science will always prevail, chipping away at the unknown until nothing remains. Others counter that certain truths might be inherently unobservable, locked behind horizons of scale or complexity we can't breach. The multiverse hypothesis, for instance, suggests whole realms of existence forever cut off from our view. Does that make them less real or just beyond our reach? Yet there's a strange beauty in this uncertainty. The fact that the universe keeps surprising us, that it refuses to fit neatly into our models, is what makes science alive and thrilling. Every anomaly is an invitation to rethink, to imagine bigger. Perhaps the answer isn't to despair at our limits, but to embrace them as part of the journey. After all, the night sky didn't become less wondrous when we learned stars weren't just dots on a celestial sphere. It became infinitely more so. In the end, the crisis in cosmology isn't just about galaxies and equations. It's about what it means to seek truth in a universe that may never fully reveal itself. And maybe that's the most human lesson of all, the courage to keep asking questions, even when the answers redefine everything we thought we knew. Science has always been a story of revolutions disguised as evolution's quiet moments when the foundations crack and everything we thought we knew gets rewritten. Take Isaac Newton's towering legacy. For over 2 centuries, his laws of motion and universal gravitation seemed unshakable, perfectly predicting the orbits of planets and the arc of cannonballs. But by the late 19th century, tiny anomalies began piling up. Mercury's orbit wobbled slightly off Newton's predictions, and experiments with light defied classical physics. Scientists didn't panic. They assumed these were minor puzzles, gaps that would eventually fit into the existing framework. Then came Einstein, a patent clerk with a wild idea. What if gravity isn't a force at all, but the curvature of space-time itself? Relativity didn't just tweak Newton's laws, it replaced them entirely, rewriting the rules of the cosmos in one breathtaking stroke. The same pattern repeats throughout history. Before Darwin, life's diversity was neatly explained by divine design, until fossils and finches revealed the messy, improvisational dance of natural selection. Before quantum mechanics, atoms were imagined as tiny billiard balls, until particles started behaving like waves and appearing in 2 places at once. Each time the old guard resisted, Lord Kelvin famously declared physics nearly complete, just years before relativity and quantum theory shattered that illusion. The lesson: scientific revolutions rarely announce themselves with fanfare. They begin as whispers, as inconsistencies too small to notice until suddenly they're impossible to ignore. Today's cosmological crisis mirrors these pivotal moments. Dark matter's stubborn invisibility, dark energy's inexplicable push, the Hubble tension's refusal to resolve. They're not just loose threads. They're the frayed edges of a tapestry that might need reweaving. And while it's tempting to assume we'll find answers within our current models, history suggests otherwise. The next Einstein could be alive right now, scribbling equations on a chalkboard somewhere, dreaming up a theory that renders dark matter obsolete or redefines gravity itself. But here's what makes this moment different. We've never had so much data or so many ways to test bold ideas. When Einstein proposed relativity, it took years to confirm with a solar eclipse. Today, telescopes like Euclid and the SKA can probe the universe's secrets in real time, hunting for deviations from relativity or traces of exotic particles. The difference between past revolutions and now is like comparing a candle to a spotlight. We're not groping in the dark anymore, but staring straight into the abyss, waiting for it to stare back. The real question isn't whether cosmology will shift, it's how radical that shift will be. Will we tweak our equations or tear them up entirely? One thing's certain, the universe has never cared about our comfort zones. And that's the thrill of it. Every anomaly is a gift, a chance to glimpse the next layer of reality. After all, the greatest discoveries don't come from confirming what we already know. They come from daring to ask what we've missed. Sometimes the most groundbreaking solutions come from tearing down the walls between disciplines. When physics stumbles at cosmic scales, it might not need better physics, but better math, or even entirely new ways of connecting seemingly unrelated fields. Take the mystery of black hole entropy, where thermodynamics, the science of heat and energy, collided with quantum mechanics in the most unexpected way. Jacob Bekenstein and Stephen Hawking showed that black holes aren't just gravitational monsters. They have temperature, they emit radiation, they behave like thermal objects. This revelation didn't come from staring deeper into a telescope, but from borrowing equations from steam engines and applying them to the edge of space-time. Now imagine applying that same cross-pollination to today's cosmic crises. Dark matter's elusiveness, for instance, might not yield to bigger particle colliders, but to insights from information theory, the mathematics of how data is stored and transmitted. Some theorists suggest dark matter could be a kind of cosmic noise, a background signal we've been misinterpreting. Others explore whether entanglement, quantum mechanics' spooky link between particles, might scale up to galactic distances, weaving invisible connections that mimic dark matter's gravitational pull. These aren't fringe ideas, they're the inevitable result of letting different branches of science cross-fertilize. Even geometry could hold unexpected keys. Einstein taught us that gravity is the curvature of space-time, but what if that curvature follows rules we haven't discovered yet? Mathematicians studying exotic shapes like Calabi-Yau manifolds, twisted, multi-dimensional spaces might stumble onto equations that redefine how gravity operates on cosmic scales. It's like realizing the universe isn't a flat map but an origami sculpture, with folds and creases hiding forces we never thought to measure. The takeaway: breakthroughs rarely come from working harder within the same box. They emerge when someone dares to carry tools from one field into another, cracking problems sideways. As we face cosmology's greatest puzzles, the solution might not lie in a deeper dive but in a wider lens, and that's where the real adventure begins. Imagine sifting through a mountain of sand one grain at a time, searching for a single speck with a unique shape. That's the scale of the challenge cosmologists face when analyzing the universe's data. Telescopes like Euclid and the Vera Rubin Observatory are flooding researchers with petabytes of information, images of billions of galaxies, maps of cosmic web filaments, flickers of distant supernova, far more than any human team could process in a lifetime. This is where artificial intelligence steps in, not as a replacement for scientists, but as a cosmic magnifying glass, revealing hidden patterns in the noise. Machine learning algorithms trained on simulated universes can spot galactic oddities or gravitational lensing distortions that human eyes might overlook, like finding a needle in a galaxy-sized haystack. Take the hunt for dark matter. Traditional methods rely on painstakingly mapping galaxy rotations or gravitational effects, but AI can analyze millions of galaxies at once, identifying subtle correlations that hint at dark matter's distribution. In 2020, a neural network named Dark Emulator stunned researchers by predicting the clustering of dark matter halos with near-perfect accuracy after training on just a fraction of the data humans would need. It's as if the algorithm absorbed the universe's hidden rulebook, intuiting connections no equation had yet captured. Similarly, AI has flagged peculiar galaxies with strange rotation curves, some moving in ways that challenge even modified gravity theories. These aren't just digital curiosities, they're breadcrumbs leading toward new physics. But AI's potential goes beyond pattern recognition. Generative models like those behind deepfake videos are now simulating entire universes in seconds. By tweaking parameters altering dark energy's strength or gravity's behavior at cosmic scales, these virtual cosmologies let researchers test thousands of alternate realities, comparing them to our own. A team at the Flatiron Institute recently used this approach to explore a radical idea. What if dark matter interacts with itself? Their AI-generated universes revealed that self-interacting dark matter could produce galaxies with cores less dense than standard models predict a match for some real-world observations. It's like having a cosmic lab where you can rerun the Big Bang with different settings, probing which versions birth a universe like ours. Yet for all its power, AI comes with caveats. Machine learning is only as good as the data it's fed. Biases in simulations can lead algorithms astray, like a parrot memorizing phrases without understanding them. In 2022, an AI famously discovered a new type of galaxy cluster until astronomers realized it had simply learned to mimic flaws in the training data. And while AI excels at finding anomalies, it can't yet explain why they occur. A neural network might flag a strange quasar alignment, but unraveling its meaning still requires human intuition and theoretical grit. The real promise lies in collaboration, human curiosity guiding AI's brute force analysis. Projects like the Sloan Digital Sky Survey now blend machine learning with traditional observation, using AI to prioritize telescope targets or clean up noisy signals. Future missions might deploy AI in real time, adjusting observations mid-scan to chase unexpected cosmic whispers. Some theorists even speculate that AI could one day propose entirely new physical laws, formulating equations that transcend human biases. Will algorithms crack cosmology's code? Perhaps not alone, but they're already reshaping how we explore the unknown. In a universe drowning in data, AI isn't just a tool, it's a new kind of partner, helping us ask questions we hadn't even dreamed of. And that's where the next revolution might begin, not in the stars, but in the silent hum of a server farm, where machines and minds together inch closer to the universe's best-kept secrets. When a single telescope costs more than $10 billion, it's hard not to wonder, are we spending wisely, or are we mortgaging the future of science itself? Projects like the James Webb Space Telescope or the upcoming Extremely Large Telescope represent humanity's grandest ambitions, pushing the boundaries of what we can see and know. Yet their staggering price tags could fund thousands of smaller experiments, each with the potential to stumble upon revolutionary discoveries. History shows us that breakthroughs often come from unexpected places: a humble lab, a graduate student's side project, or an experiment deemed too risky for mainstream funding. The discovery of cosmic microwave background radiation, the bedrock of Big Bang cosmology, wasn't the result of a meticulously planned megaproject, but an accidental finding by radio astronomers studying pigeon interference. The tension between big and small science isn't just about money, it's about diversity of thought. When funding funnels into a handful of colossal endeavors, entire avenues of research can wither. Imagine if all medical research focused solely on curing cancer while ignoring antibiotics or vaccines. Similarly, cosmology's obsession with dark matter detectors and space telescopes might leave radical alternatives like modified gravity or emergent spacetime theories starved of resources. The irony, some of these fringe ideas could hold the key to solving the very mysteries big science aims to crack. But dismissing megaprojects as wasteful misses their irreplaceable value. They're not just tools, they're engines of inspiration. The Hubble Deep Field image, which revealed thousands of galaxies in a patch of sky no bigger than a grain of sand, didn't just advance science, it redefined humanity's place in the cosmos. These endeavors also create technologies with ripple effects far beyond astronomy. The detectors developed for the Laser Interferometer Gravitational Wave Observatory LIGO are now refining quantum computing, while space telescope optics have revolutionized medical imaging. The challenge isn't choosing between big and small science, but striking a balance funding moonshots while leaving room for the wild ideas that could change everything. Critics argue that billion-dollar telescopes divert funds from pressing earthly crises: climate change, poverty, disease. Yet this framing assumes a zero-sum game, as if defunding cosmology would automatically channel money toward social good. In reality, scientific budgets are a tiny fraction of global spending, dwarfed by military expenditures or corporate subsidies. The real question isn't whether we can afford these projects, but whether we can afford not to pursue them. Curiosity isn't a luxury, it's the spark that has driven every human advancement. When Galileo pointed his telescope at Jupiter's moons, he wasn't solving famine or plague. He was igniting a revolution that would reshape civilization. The solution may lie in rethinking how science is funded. Instead of winner-takes-all grants, we could adopt staggered investment, where risky ideas get small seed funding, and only those showing promise scale up. The private sector's approach to startups, where many small bets lead to a few transformative successes, could be a model. Meanwhile, megaprojects could share infrastructure and data more openly, turning instruments like the Vera Rubin Observatory into collaborative platforms for thousands of researchers. In the end, this isn't just about telescopes or dark matter. It's about what kind of future we want to build, one where only the safest ideas get heard, or one where curiosity, in all its forms, has room to thrive. The universe doesn't reveal its secrets to those who play it safe. Whether through the lens of a $10 billion telescope or a homemade spectrometer, discovery demands both ambition and humility, the courage to reach for the stars, and the wisdom to listen to the quietest whispers in the dark. You might think cosmology is just about distant galaxies and abstract equations, but its fingerprints are all over your daily life. Take the GPS in your phone without Einstein's theory of relativity. Those turn-by-turn directions would be off by miles. Satellites orbiting Earth experience time slightly faster than we do on the ground. And if engineers didn't account for this cosmic quirk, your navigation app would lead you into a lake instead of the grocery store parking lot. This isn't just a neat trick of physics, it's proof that understanding the universe isn't some ivory tower pursuit. It's the reason you don't get lost on road trips. Beyond practical tech, cosmology reshapes how we see ourselves. When the Hubble telescope beamed back its iconic, pale blue dot image showing Earth as a speck in the vastness of space, it didn't just advance science. It sparked a cultural shift, humbling our planet's place in the cosmos and fueling environmental movements. Artists, poets, and philosophers have drawn inspiration from these cosmic perspectives, wrestling with questions that science alone can't answer. Are we alone? What does it mean to exist in a universe so immense? Even religions have reinterpreted ancient texts in light of the Big Bang. finding harmony between creation myths and cutting-edge astrophysics. Then there's the raw, driving force of curiosity. Every child who stares at the night sky and wonders what's out there is tapping into the same impulse that built civilizations. The desire to explore, whether it's mapping the ocean or launching a telescope, is baked into human DNA. Cosmology doesn't just satisfy that itch, it amplifies it. The hunt for dark matter has led to breakthroughs in quantum computing. The study of black holes has revolutionized medical imaging. When we chase the universe's biggest mysteries, we invent tools that transform life on Earth, often in ways no one could predict. But here's the real magic. Cosmology reminds us that we're part of something grander. The calcium in your bones, the iron in your blood, these elements were forged in the hearts of dying stars. You're literally made of stardust, a walking testament to the universe's creativity. That connection isn't just poetic, it's a call to keep looking up, to keep asking questions. Because every time we unravel a cosmic secret, we don't just learn about the universe, we learn about ourselves. Dark energy often gets slapped with the label anti-gravity, a catchy but dangerously misleading metaphor that warps public understanding. Unlike gravity's familiar pull, dark energy doesn't push matter away like some cosmic repeller. Instead, it's the fabric of space itself that's stretching, carrying galaxies apart like raisins in an expanding loaf of bread. Picture this: if gravity is a magnet drawing objects together, dark energy isn't an opposing magnet flinging them apart. It's more like the table beneath the magnets quietly growing larger, making the distance between them increase without any force acting on them directly. This distinction isn't just semantics, it's the difference between a force and a property of spacetime. Gravity, whether Newton's or Einstein's version, arises from mass warping the geometry of the universe. Dark energy, on the other hand, is baked into the vacuum of space, a latent energy that causes spacetime to expand at an accelerating rate. When scientists say the universe's expansion is speeding up, they're not claiming galaxies are being pushed apart by some invisible shove. They're observing that the space between galaxies is stretching faster over time, like a rubber sheet being pulled tauter by an unseen hand. The anti-gravity myth fuels pseudoscientific claims, from exaggerated doomsday scenarios to wild theories about energy fields defying physics. In reality, dark energy's effects are subtle. It dominates only on cosmic scales where matter's gravity is weakest. Within galaxies or even clusters, gravity's pull still reigns supreme. That's why the Milky Way isn't being torn apart. Our local gravitational bonds easily overpower dark energy's feeble influence. Only in the vast voids between galactic superclusters, where matter is sparse, does dark energy's stretch become noticeable. Clarifying these nuances matters because language shapes how we grapple with cosmic mysteries. When documentaries or headlines frame dark energy as a mysterious repulsive force, they obscure the real puzzle. Why does empty space have this inherent tendency to expand? The answer might lie in quantum fields, higher dimensions, or something entirely unforeseen, but conflating it with gravity's opposite only muddies the waters. Science thrives on precision, and every blurred definition is a missed opportunity to inspire the next generation of thinkers to explore deeper. So next time you hear dark energy described as anti-gravity, remember, the universe isn't playing tug of war. It's unfolding in ways we're still learning to measure, one stretch of spacetime at a time. We humans are prisoners of our own senses. Evolution crafted our eyes to spot ripe fruit in trees, not to perceive the invisible scaffolding of the cosmos. Consider the humble bat navigating the world through echolocation, or the mantis shrimp with its 16 color receptors, experiencing hues we can't even name. Our biological toolkit is spectacularly mismatched for cosmic detective work, especially when hunting something as elusive as dark matter. Unlike stars that blaze across telescopes or planets that reflect sunlight, dark matter doesn't interact with light at all. It doesn't absorb it, scatter it, or glow in its presence. If you held a chunk of dark matter in your hand, assuming you could, it would be utterly transparent, colder than space itself, slipping through your fingers like ghostly smoke. This isn't just a technological hurdle, it's a philosophical one. For centuries, science has relied on observation and experimentation. But what happens when the phenomenon we're studying refuses to play by those rules? Dark matter's refusal to perform for our instruments forces us to confront an uncomfortable truth. Some aspects of reality might forever remain beyond direct experience. We're like ants trying to comprehend a thunderstorm. We feel the vibrations, see the aftermath, but the storm itself operates on scales and principles alien to our tiny world. Yet, absence of evidence isn't evidence of absence. Just because we can't see dark matter doesn't mean we can't know it. Think of a windless day. You can't see the air, but watch a leaf tremble, a kite soar, and you know it's there. Dark matter announces itself through gravity's fingerprints, the way galaxies spin too fast, how light bends around cosmic voids, the intricate web of the universe's large-scale structure. These aren't guesses, they're measurements so precise they've convinced even the staunchest skeptics. The real breakthrough might come from embracing our limitations. Instead of straining to see dark matter with tools built for light, we're learning to listen to the cosmos in new ways. Particle detectors buried deep underground wait for the faintest tremor of a dark matter particle colliding with ordinary atoms. Telescopes like Euclid map the universe's distortion, tracing dark matter's shadow through gravitational lensing. Even quantum sensors, chilled to near absolute zero, hunt for minuscule ripples in spacetime's fabric. These aren't failures of imagination, they're triumphs of ingenuity, proving science doesn't need direct observation to uncover truth. Perhaps the most humbling lesson is this: the universe owes us no clarity. It doesn't care if its secrets fit neatly into human categories of sight, sound, or touch. Some truths are written in wavelengths beyond our perception, or whispered through forces we've yet to name. And that's the beauty of the hunt, not in the certainty of capture, but in the thrill of the chase, the slow unraveling of a mystery that reminds us how much wonder still lies beyond the edges of our understanding. The numbers in our universe's blueprint seem impossibly fine-tuned. Adjust gravity by a fraction, and stars would never ignite. Tweak the strong nuclear force slightly, and atoms couldn't form. Even the cosmological constant, that mysterious driver of cosmic acceleration, balances on a knife's edge, too strong, and galaxies tear apart before life emerges, too weak, and the universe collapses into a black hole. This eerie precision has haunted scientists for decades. Are these constants fundamental laws, or cosmic lottery numbers we just happen to draw? Enter the Anthropic Principle, the idea that we observe these Goldilocks conditions simply because we're here to observe them. In other words, if the universe weren't hospitable to life, no one would be around to question it. It's like a puddle marveling at how perfectly its hole fits its shape, oblivious to the fact that the water molded itself to the cavity, not the other way around. Proponents argue this isn't a cop-out but a statistical inevitability. If a near-infinite array of universes exist, each with different physical parameters, ours isn't special. It's just the one where the dice landed in life's favor. Critics, though, dismiss this as a metaphysical shrug, a way to sidestep deeper questions. If we accept the Anthropic Principle as an explanation, they argue, we risk slamming the door on discovery. After all, science thrives on asking why. Why is the electron's mass what it is? Why does space-time have 4 dimensions? To chalk it all up to observer selection feels like surrendering to mystery. Even more damning, the principle is notoriously hard to test. Unlike dark matter or inflation, which make measurable predictions, the anthropic principle often retreats into untestable abstraction, leaving some to wonder if it's philosophy masquerading as physics. Yet the debate reveals cosmology's existential tension. On one side, the multiverse hypothesis, where every possible constant plays out across countless universes, turning fine-tuning into a numbers game. On the other, the quest for a theory of everything that might derive these constants from first principles, rendering the anthropic principle unnecessary. String theory, for instance, dreams of a mathematical framework where constants aren't arbitrary but emerge from deeper symmetries. But after decades, no such theory has delivered, leaving the anthropic principle to linger in the gap between observation and understanding. Perhaps the truth lies in the middle. The anthropic principle might not be an answer but a signpost, pointing toward deeper layers of reality we've yet to uncover. After all, every scientific revolution begins with anomalies, facts that don't fit the current paradigm. Whether this cosmic fine-tuning hints at a multiverse, a deeper law, or something beyond our current imagination, one thing's certain: the universe keeps whispering that we're missing something profound. And in that uncertainty, science finds its most thrilling questions. The night sky has never been just a canvas of stars. It's a mirror reflecting humanity's deepest fears, dreams, and stories. Long before telescopes revealed the true scale of the cosmos, ancient cultures wove myths around celestial bodies, turning wandering planets into gods and constellations into epic tales. The Greeks saw Orion the hunter forever chasing the Pleiades across the heavens, while Aboriginal Australians traced the emu in the dark, its silhouette formed by the dust lanes of the Milky Way. These weren't just attempts to explain the unknown, they were acts of meaning-making, transforming cold, distant lights into narratives that resonated with human experience. Fast forward to the modern era, and cosmology's influence on creativity has only deepened. Science fiction, from H.G. Wells' War of the Worlds to Interstellar's time-bending black hole gargantua, doesn't just borrow from astrophysics, it grapples with its implications. When Arthur C. Clarke imagined a monolith on the moon in 2001, a space odyssey, he tapped into the eerie grandeur of cosmic mystery, the idea that we might not be alone in a universe vaster than comprehension. These stories aren't escapism, they're thought experiments, asking how humanity might confront the sublime terror of infinity or the existential humility of being a speck in the void. Even religious and spiritual traditions have evolved alongside cosmic discovery. The Big Bang Theory, once met with resistance, now finds echoes in creation myths that speak of a universe born from a single, explosive moment. Some theologians argue that dark matter's invisibility parallels mystical concepts of the divine present everywhere yet undetectable by ordinary means. Meanwhile, the Hubble telescope's Pillars of Creation photo, with its towering clouds of stellar nursery gas, has been compared to Renaissance paintings of biblical scenes, blending scientific awe with spiritual reverence. Artists, too, have translated cosmic data into visceral experiences. Composers like John Cage used star maps to generate musical scores, while visual creators like Katie Patterson embed meteorite dust into sculptures or broadcast live signals from dying stars. These works don't just represent the cosmos, they invite us to feel it, bridging the gap between abstract equations and human emotion. Consider the Journey to the Edge of the Universe installation, where visitors walk through a tunnel of projected galaxies, each step representing 1,000,000 light years, a tangible reminder of our fleeting place in cosmic time. What unites these creative responses is a shared impulse, to make the universe personal. Whether through a sci-fi novel's alien encounter or a painter's interpretation of quantum foam, art and storytelling transform cosmology from a distant science into a shared human adventure. They remind us that every equation describing dark energy is also a riddle about our origins, every black hole simulation a meditation on the unknown. In the end, the stars don't just light up the sky, they ignite imagination, proving that science and creativity aren't opposites, but partners in the eternal dance to understand our place in the cosmos. The story of science isn't just one of meticulous planning and rigid hypotheses, it's also a tale of happy accidents and unexpected detours. Take the cosmic microwave background, that faint echo of the Big Bang. In 1965, Arno Penzias and Robert Wilson weren't searching for the origins of the universe. They were just trying to calibrate a radio antenna for Bell Labs. But no matter how they adjusted it, an annoying static persisted, a uniform hiss coming from every direction in the sky. After eliminating every possible source, from pigeon droppings to faulty wiring, they stumbled onto the truth. They'd found the afterglow of creation itself, a discovery that would win them the Nobel Prize and revolutionize cosmology. This isn't an exception, it's the rule. X-rays were discovered when Wilhelm Röntgen noticed a mysterious glow from a screen he hadn't intended to illuminate. Penicillin emerged because Alexander Fleming left a Petri dish uncovered, allowing mold to contaminate his bacterial samples. Even the Hubble Space Telescope's famous deep field image, which revealed thousands of previously unseen galaxies, was a gamble. Astronomers pointed the telescope at what seemed like an empty patch of sky, betting on the unknown. Science's greatest leaps often come not from looking where we expect, but from stumbling into the unexplored. The lesson: rigidity is the enemy of discovery. When researchers become too wedded to their models, when they dismiss anomalies as noise rather than clues, they risk missing the next big breakthrough. The Hubble tension, dark matter's elusiveness, even the strange behavior of cosmic voids, these aren't just problems to solve. They're invitations to stay curious, to embrace the possibility that the universe might be weirder, messier, and more wonderful than our theories predict. So where does the next revelation lie? Maybe in a grad student's overlooked data set, or in the static of a telescope tuned to the wrong frequency. Perhaps it's hidden in the margins of a failed experiment, waiting for someone to ask, what if we've been asking the wrong question all along? The history of science whispers a truth we do well to remember. Sometimes the most profound truths reveal themselves only when we're willing to get delightfully, productively lost. Science thrives on a paradox. Collaboration and competition aren't opposites, but two sides of the same cosmic coin. Picture the hunt for the Higgs boson. Thousands of physicists across dozens of countries pooled data, resources, and brainpower at CERN. Yet individual teams raced to analyze results first, each hoping to make the breakthrough. This tension isn't unique to particle physics. Cosmology's biggest mysteries: dark energies push, dark matters pull. The Hubble tension demands global cooperation while still benefiting from the fire of friendly rivalry. Take the Sloan Digital Sky Survey, one of history's most ambitious celestial maps. Astronomers from over 50 institutions contributed observations, creating a shared treasure trove of galactic data. But within that collaboration, smaller teams compete to mine insights faster, publishing papers that build on, and sometimes challenge, each other's work. It's like a group of chefs sharing the same kitchen. They might swap ingredients and techniques, but each strives to craft the most groundbreaking dish. This dynamic accelerates discovery, ensuring no single perspective dominates and errors get caught in the crossfire of peer scrutiny. Yet the balance is delicate. When proprietary data gets hoarded or credit disputes arise, progress stalls. The infamous Bicep 2 incident, where a team prematurely claimed evidence of cosmic inflation, only to realize their signal was galactic dust, underscores the risks of rushing to beat rivals. Conversely, projects like the Event Horizon Telescope, which united 8 observatories to capture the first black hole image, prove how collaboration can achieve the impossible. By openly sharing algorithms and calibrations, scientists turned Earth into a planet-sized telescope, a feat no single facility could match. The rise of open access platforms like RZIV and Zenodo has transformed this dance. Today, a grad student in Mumbai can analyze data from a Chilean telescope, then compare notes with a professor in Chicago, all within hours. But competition hasn't vanished, it's shifted. Instead of racing to gather data, teams now sprint to interpret it, with preprint servers letting ideas spread faster than ever. This new ecosystem rewards creativity and rigor, not just resource access, leveling the playing field for smaller institutions. Still, challenges linger. Funding agencies often prioritize flashy solo breakthroughs over incremental teamwork, while academic tenure systems disproportionately reward first authorships. Some propose radical fixes: team science, grants that recognize collective contributions, or blockchain-like systems to track individual inputs in massive collaborations. Others argue competition itself needs reframing, not as a zero-sum game, but as a collective striving toward shared horizons. The most exciting discoveries often emerge at this intersection. When the Planck and WMAP teams independently mapped the cosmic microwave background, their slight discrepancies forced deeper scrutiny, refining our universe's age to unprecedented precision. Their rivalry wasn't a barrier, it was a whetstone, sharpening the edge of collective knowledge. In the end, cosmology's greatest strength lies in its ability to hold these forces in tension, the camaraderie of shared curiosity, and the spark that ignites when brilliant minds push each other further. The universe, after all, doesn't care who cracks its secrets, only that we never stop trying. The crisis in cosmology isn't a sign that science is broken, it's proof that science is working exactly as it should. Think of it like a detective story where every dead end isn't a failure, but a chance to reevaluate the clues. For centuries, we've built our understanding of the universe brick by brick, only to occasionally hit a wall where the bricks no longer fit. Dark matter's ghostly presence, dark energy's relentless push, the Hubble tension's stubborn divide. These aren't roadblocks, they are signposts screaming that there's something beyond our current grasp. History teaches us that the most profound breakthroughs emerge from moments just like this. When Newton's laws couldn't explain Mercury's orbit, it wasn't the end of physics, it was the dawn of relativity. When quantum particles refused to behave like tiny billiard balls, it wasn't a failure. It was the birth of an entirely new way to see reality. Today's cosmological puzzles are no different. The universe isn't taunting us, it's inviting us to dig deeper, to think wilder, to imagine beyond the limits of our textbooks. So where do we go from here? The answers might come from a direction we least expect. Maybe dark matter isn't a particle but a flaw in our understanding of gravity's fabric. Maybe dark energy isn't a constant but a shifting force, evolving as the cosmos expands. Or perhaps the solution lies in a theory so radical it hasn't even been dreamed up yet, a paradigm shift that will make our current models look as quaint as epicycles. The tools we're building today, telescopes like Euclid and the Vera Rubin Observatory, AI-driven simulations, quantum gravity experiments, are more than just instruments. They're keys to doors we don't even know exist, and the beauty of this moment is that we don't need to have all the answers right now. The thrill is in the chase, the slow unraveling of a mystery that's been unfolding for 13.8 billion years. So stay curious, question everything, because the greatest discoveries aren't just about finding answers, they're about learning how to ask better questions. And if history's any guide, the universe still has plenty of surprises left in store. The next chapter of cosmology isn't written yet. Who knows, maybe you'll be the one to